After 18 billion kilometers and 45 years of travel, Voyager 1 made a discovery that sent shockwaves through the scientific community. Our solar system has a definitive edge, and what lies beyond it is unlike anything we've ever encountered. This wasn't supposed to happen. These twin spacecraft were designed to study Jupiter and Saturn for just 4 years before shutting down forever. Instead, they became humanity's first ambassadors to interstellar space. Equipped with 1970s technology more primitive than a modern calculator, yet still transmitting data from the most remote human-made objects in existence. In the late 1970s, NASA prepared for one of the most daring missions in the history of space exploration. Two identical spacecraft, later named Voyager 1 and Voyager 2, were built to seize a once-in-a-lifetime opportunity. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were aligned in such a way that a single spacecraft could use their gravity to slingshot from one world to the next. This planetary lineup happens only once every 176 years, and if NASA missed it, humanity would not get another chance until the 22nd century. Voyager 2 launched first in August of 1977, followed shortly after by Voyager 1 in September. Although Voyager 1 was launched later, its faster trajectory allowed it to overtake its twin and reach Jupiter first. From the moment these spacecraft left Earth, they were already part of history. The mission was ambitious, but modest in its official goals. The Voyagers were only guaranteed to last 5 years, long enough to capture detailed images and measurements of Jupiter and Saturn. Everything beyond that would be considered a bonus. To many inside NASA, it seemed unlikely that the probes would survive the harsh conditions of deep space for very long. Yet the engineers behind them quietly prepared for the possibility of a much longer journey. Each spacecraft was packed with redundant systems, so that if one component failed, another could take its place. They carried advanced instruments for the time, including high-resolution cameras, magnetometers, plasma detectors, and cosmic ray sensors. And most importantly, they were powered not by solar panels, which would be useless in the dim outer solar system, but by radioisotope thermoelectric generators. These RTGs use the heat from decaying plutonium-238 to generate electricity, a steady and reliable source of power that would allow the probes to operate far from the warmth of the sun. The design was rugged and forward-looking. The spacecraft's body was covered in insulation to endure the freezing darkness of interplanetary space. Their massive dish antennas, more than 3 meters wide, were engineered to beam signals across billions of kilometers back to Earth's deep space network. Even with this technology, by the time Voyager reached the edge of the solar system, its signal would be weaker than a household refrigerator light bulb, yet still detectable. What makes this even more remarkable is the sheer longevity of the technology. Built in the era of cassette tapes, rotary phones, and early computers, the Voyagers were essentially equipped with memory and processing power far less than that of a modern smartphone. Yet, through ingenuity and careful planning, NASA created 2 spacecraft capable of outlasting generations of human technology. At the time of their launch, no one could have predicted just how far the Voyagers would go, or how many discoveries they would bring. They were sent out as planetary explorers, but they would become something far greater, the first human-made objects to journey into interstellar space. When Voyager 1 and Voyager 2 left Earth in 1977, they carried with them some of the most advanced technology humanity had ever placed into space. But by today's standards, their equipment was incredibly simple. Their total computing power was less than the chip inside a basic digital watch. And yet, that simplicity became part of their strength. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. At their core, the Voyagers were marvels of redundancy. Each carried multiple computers, not for speed or multitasking, but as backups in case of failure. If one computer glitched or shut down, another could immediately take over. This design decision has been crucial in keeping both spacecraft alive for nearly half a century. For storing data, the Voyagers used something almost unimaginable today: 8-track digital tape recorders. These reels of magnetic tape spun in deep space, capturing the probe's priceless observations before slowly transmitting them back to Earth. Each tape could hold about 500 megabits of data, a tiny fraction of a modern USB stick. Yet, every byte was precious. Engineers had to carefully plan which images and measurements to record, because storage space and bandwidth were so limited. The imaging systems, however, were cutting edge for their time. Each Voyager was equipped with a pair of cameras, a wide angle for sweeping shots of planets and moons, and a narrow angle for zooming in on fine details. These cameras used Vidicon tubes, technology borrowed from television cameras, to convert light into electronic signals. Despite their limitations, they produced some of the most iconic images in the history of space exploration. But it wasn't just about instruments. The Voyagers were built to endure the brutal conditions of deep space. Beyond Mars, sunlight is too weak for solar panels to work efficiently. Temperatures plunge to hundreds of degrees below freezing. Cosmic radiation bombards every surface. To survive, the spacecraft were wrapped in protective insulation, and their instruments were shielded against radiation damage. Power came from their radioisotope thermoelectric generators, steady, compact nuclear batteries that converted heat from decaying plutonium into electricity. At launch, each Voyager had enough power to run all of its systems comfortably. Over time, as the plutonium decayed, the available power dropped. To conserve energy, NASA's engineers gradually began shutting down non-essential instruments. Even so, after 47 years in space, both probes are still running, a testament to their durable design. Perhaps most extraordinary of all is the communication system. Each spacecraft is equipped with a large high-gain antenna, more than 3 meters across, built to send and receive signals across the solar system. Today, Voyager 1 is more than 20 billion kilometers away, so far that it takes over 22 hours for a radio signal to travel from Earth to the spacecraft. By the time its faint whisper of a signal reaches home, it is weaker than the static background noise of the universe. And yet, thanks to the immense sensitivity of NASA's Deep Space Network, a global array of radio antennas, we can still hear it. This delicate balance of rugged engineering and clever design ensured that the Voyagers could keep working long after their planned lifespans. What began as a mission measured in years has turned into a mission measured in decades. And against all odds, these twin spacecraft are still faithfully sending back data, pushing the boundaries of human exploration farther than anyone in the 1970s could have imagined. By 1979, Voyager 1 and Voyager 2 had reached their first great destination, Jupiter, the largest planet in the solar system. Until then, Jupiter had only been seen through telescopes and by the earlier Pioneer probes, which provided the first rough glimpses of the gas giant. But nothing could prepare scientists for the incredible detail that the Voyagers would deliver. As the spacecraft closed in, their cameras began transmitting a steady stream of images back to Earth. For the first time, humanity saw Jupiter not as a distant disk in the night sky, but as a living, dynamic world. The iconic Great Red Spot, a storm larger than Earth itself, was revealed in sharp detail, swirling with turbulent clouds and changing more rapidly than expected. Around the planet, entire systems of bands and storms shifted and evolved, showing that Jupiter's atmosphere was far more active than anyone had imagined. But the real surprises came from Jupiter's moon. Among the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, Voyager uncovered landscapes unlike anything in the solar system. The biggest shock came from Io. Instead of being a cold, dead world as many had assumed, Io was alive with activity. Voyager's cameras caught enormous plumes rising hundreds of kilometers above its surface, the unmistakable signature of volcanoes erupting in real time. This was the first direct evidence of active volcanism beyond Earth, and it immediately made Io the most volcanically active body in the solar system. Its surface was painted in bizarre yellows, oranges, and reds from sulfur and lava flows, constantly reshaped by eruptions. Then came Europa. Its surface appeared smooth and bright, crisscrossed with dark cracks and ridges, but almost no impact craters. This suggested that Europa's surface was young and constantly being renewed. The patterns looked like ice sheets that had broken apart and refrozen, leading scientists to propose a stunning possibility. Beneath Europa's frozen crust might lie a vast global ocean of liquid water. That idea alone transformed Europa into one of the most promising places in the solar system to search for life. Voyager also discovered that Jupiter has a faint ring system, invisible from Earth at the time, though delicate and dim compared to Saturn's majestic rings. This was an unexpected find that proved ring systems were more common than once believed. In addition to the Galilean moons, the Voyagers spotted several new, smaller moons orbiting Jupiter, each with unique and varied geologies. This expanded Jupiter's growing family of satellites and gave scientists fresh worlds to study. Beyond the moons and rings, the Voyagers also measured Jupiter's magnetosphere, the largest and most powerful magnetic field of any planet in the solar system. The probes discovered that this vast magnetic bubble stretches millions of kilometers into space, trapping radiation and charged particles. It was so intense that it posed a serious hazard to the spacecraft themselves, forcing engineers to design special shielding just to survive the encounter. The Jupiter flybys were a triumph. In just a few weeks, the Voyagers transformed Jupiter from a distant dot into a world teeming with storms, volcanic activity, hidden oceans, and unexpected rings. These discoveries didn't just rewrite textbooks. They reshaped how scientists thought about planets and moons. For the first time, it was clear that the outer solar system was full of dynamic, active worlds, not lifeless rocks. Jupiter had delivered far more than NASA had hoped, and it was only the beginning. With their instruments still healthy and their trajectories set, the Voyagers prepared to aim for their next great destination, the jewel of the solar system, Saturn. After their historic encounters with Jupiter, the Voyager spacecraft pressed onward to their next great target, Saturn, the jewel of the solar system. To the naked eye, Saturn had always stood out because of its dazzling ring system, but until the Voyagers arrived, no one truly understood just how complex and beautiful those rings really were. When Voyager 1 arrived at Saturn in late 1980, its cameras revealed something astonishing. The planet's rings were not solid, smooth bands as many had once imagined. Instead, they were made up of hundreds of thin ringlets, delicate strands woven together in intricate patterns. Within these rings, the spacecraft found subtle gaps and waves, evidence that Saturn's gravity and the pull of tiny nearby moons was constantly shaping them. This led to the discovery of shepherd moons, these small moons orbiting near. The rings acted like cosmic sculptors, using their gravity to herd and confine the ring particles, keeping the edges sharp and distinct. Suddenly, Saturn's rings were not just a feature, but a dynamic, living system shaped by an ongoing dance between moons and dust. The Voyagers also turned their instruments on the planet itself. They observed atmospheric bands and storms, though subtler than Jupiter's, and they measured Saturn's powerful magnetic field, which traps charged particles in much the same way Earth's field protects us, but on a far greater scale. Perhaps the most exciting moment of Voyager 1's Saturn encounter was its flyby of Triton, Saturn's largest moon. Triton had long been of interest to scientists because telescopes on Earth suggested it might have a thick atmosphere. Voyager 1 confirmed it. Triton was wrapped in a dense, nitrogen-rich atmosphere, the only moon in the solar system known to have one. But the haze was so thick that the surface remained hidden from view. Scientists speculated that Triton might hold lakes, rivers, or even oceans of liquid hydrocarbons. Decades later, the Cassini-Huygens mission would finally confirm this, proving Titan to be one of the most Earth-like worlds in the solar system. Voyager 2 followed in 1981, offering a second close-up look at Saturn and its moon. Among its many observations, one stood out: the small, icy moon, Enceladus. At first glance, Enceladus seemed relatively unremarkable, but Voyager's cameras revealed a surface that was surprisingly smooth and bright, lacking the craters expected of such a small moon. This suggested that some kind of internal activity was reshaping it. Though the Voyagers could only hint at the truth, later missions would confirm that Enceladus harbors a subsurface ocean and shoots great geysers of water vapor into space, making it another tantalizing place to search for life. The Saturn encounters were breathtaking, but they also marked a turning point. After its close flyby of Titan, Voyager 1's trajectory sent it on a path out of the solar system, never to visit another planet. Voyager 2, however, was aimed toward an even greater journey, the first and only spacecraft to explore Uranus and Neptune. By the time the Voyagers had finished with Saturn, humanity's picture of the outer solar system had changed forever. What was once thought to be a realm of static, frozen worlds was now revealed as a place of dynamic activity, mysterious atmospheres, and moons with hidden potential. Saturn had lived up to its reputation as the jewel of the solar system, but the Voyagers were only halfway through their grand tour. While Voyager 1's journey ended with Saturn, its twin was sent on a far more ambitious path. Voyager 2 was carefully aimed to take advantage of the rare planetary alignment, slingshotting from one world to the next. This trajectory would allow it to perform the first, and so far only, close-up encounters with the two most distant giant planets in our solar system, Uranus and Neptune. In January 1986, nearly a decade after launch, Voyager 2 reached Uranus. Until that moment, Uranus had been little more than a pale green dot seen through telescopes, mysterious and featureless. Voyager's approach changed that forever. The spacecraft discovered that Uranus was surrounded by a system of faint, dark rings, invisible from Earth until then. These rings were narrow and delicate, very different from Saturn's brilliant bands. Voyager 2 also detected 10 new moons, small icy bodies orbiting the planet, each with strange shapes and surfaces sculpted by billions of years in the cold outer solar system. But the biggest surprise was Uranus itself. Voyager revealed a planet tipped on its side, rotating at an extreme tilt of 98 degrees. This odd orientation made its seasons unlike anything else in the solar system, with each pole experiencing 42 years of continuous daylight followed by 42 years of darkness. Even stranger, Uranus's magnetic field was not aligned with its axis. It was wildly tilted and offset from the planet's center. Scientists were left baffled, struggling to understand how such a strange magnetic field could exist. After Uranus, Voyager 2 pressed onto its final planetary target, Neptune. In August 1989, 12 years after leaving Earth, it became the first and only spacecraft to visit the distant blue world. From afar, Neptune appeared cold and quiet, but Voyager 2's cameras revealed a planet full of activity. It spotted massive storm systems, including the now famous Great Dark Spot, a swirling vortex nearly the size of Earth. These storms were driven by the fastest winds ever recorded in the solar system, racing at supersonic speeds of over 2,000 kilometers per hour. Neptune, once thought to be a calm ice giant, was suddenly revealed as a world of violent weather and hidden power. Like Uranus, Neptune also had a system of faint rings, thin arcs of dust that circled the planet. But the most dramatic discovery of all came from Neptune's largest moon, Triton. Instead of being frozen and inactive, Triton stunned scientists by showing signs of geological activity. Voyager 2 captured images of geysers erupting nitrogen gas high into the thin atmosphere, evidence of ongoing internal heat. Triton also orbits Neptune in the opposite direction of the planet's rotation, suggesting it may have once been a captured object from the Kuiper Belt. Its active surface made it one of the most intriguing worlds Voyager ever encountered. By the time Voyager 2 left Neptune behind, its planetary tour was complete. In just 12 years, it had explored 4 giant planets, dozens of moons, multiple ring systems, and magnetic fields unlike any ever seen before. No spacecraft since has visited Uranus or Neptune, meaning Voyager 2, Saturn-2's discoveries remain our most detailed look at these distant worlds. The extended Grand Tour had revealed a solar system far more diverse and dynamic than anyone had imagined. With its mission at the outer planets complete, Voyager 2, like its twin, now set course for the unknown, the vast frontier of interstellar space. After decades of exploring the outer planets, Voyager 1 had one final gift for humanity. In 1990, nearly 13 years after its historic flyby of Saturn, scientists faced a question posed by the legendary astronomer Carl Sagan. What would Earth look like from the edge of the solar system? At over 6 billion kilometers away, Voyager 1 was now the farthest human-made object from our planet, venturing into the silent, dark frontier of space. At Sagan's urging, the spacecraft's cameras were turned around for a final glance at home. From that staggering distance, the sun itself appeared only as a small point of light, and there, suspended in a thin ray of sunlight, was our world, a tiny, fragile, pale blue dot. In the image, Earth was smaller than a single pixel, barely distinguishable against the vastness of space. Yet, its significance was immense. That speck, barely visible, held every human, every civilization, every story, every war and peace, every triumph and tragedy in history. The pale blue dot captured the true scale of our universe, showing just how delicate and isolated our planet truly is. Sagan reflected on this image in his writings, emphasizing that all our ambitions, conflicts, and achievements occur on that tiny stage. From that perspective, borders, wealth, power, and pride appear insignificant. The photograph was a humbling reminder that humanity shares a fragile home in an immense, indifferent cosmos. Beyond its philosophical meaning, the pale blue dot image also became a cultural touchstone. It inspired generations of scientists, artists, and dreamers to look outward, to think beyond our immediate concerns, and to recognize the shared responsibility we have to protect our planet. For the first time, people could see Earth from the perspective of the universe, not as a vast dominion, but as a tiny, precious oasis of life suspended in the cosmic dark. Even decades later, the image continues to resonate. It reminds us that exploration is not just about discovery, but also about perspective. Voyager 1, in its quiet voyage through interstellar space, gifted humanity a new way to see itself, not as conquerors of space, but as caretakers of a small, beautiful world, drifting together through the vastness of the cosmos. The pale blue dot stands as a testament to curiosity, imagination, and humility. It is a moment when technology, science, and human wonder converged to show us the sheer scale of the universe and our delicate place within it. After completing their grand tour of the outer planets, both Voyager 1 and Voyager 2 began a journey into a completely unknown region, the edge of the sun's influence. This boundary, where the solar wind, a stream of charged particles flowing outward from the sun, meets the vastness of interstellar space, is called the termination shock. The termination shock is the first real wall of the solar system. As the Voyagers approached it, their instruments detected the solar wind slowing dramatically. Particles that once sped outward at millions of kilometers per hour were suddenly decelerated, compressed, and heated by the pressure of the interstellar medium. Scientists had predicted this boundary, but the reality was far more dynamic and mysterious than expected. Beyond the termination shock lies the heliosheath, a turbulent, chaotic region at the outer edge of the heliosphere. The Voyagers discovered that this area was not smooth or uniform. Instead, it is filled with strange magnetic bubbles, waves of energetic particles, and surprising plasma activity. Scientists observed ripples, eddies, and pockets, where the solar wind twists and folds, interacting with the interstellar medium in ways never fully predicted. The Voyager's instruments, including magnetometers and plasma detectors, revealed that the heliosheath is a region of intense activity, almost like a cosmic storm at the border of our solar system. The spacecraft detected sudden increases in cosmic rays, high-energy particles from outside the sun's influence, which signaled that the probes were approaching the final frontier of the sun's reach. This discovery was crucial for understanding how our solar system interacts with the galaxy around it. The heliosheath acts as a protective bubble, shielding the planets from a large portion of harmful cosmic radiation. Studying its structure has given scientists insights into how stars and their winds shape space, and how magnetic fields sculpt the edges of planetary systems across the universe. Even decades after launch, Voyager 1 and 2 continue to send back data from these remote regions, helping humanity understand a boundary no human has ever crossed. The probe's journey through the termination shock and heliosheath transformed our view of the solar system from a static bubble to a dynamic, living frontier, a boundary of constant motion, turbulence, and interaction with the wider galaxy. After years of traveling through the outer reaches of the heliosphere, Voyager 1 and Voyager 2 reached an even more monumental milestone: the heliopause, the boundary where the influence of the sun finally ends, and the vast, uncharted territory of interstellar space begins. In 2012, Voyager 1 became the first human-made object to cross this boundary. Its instruments recorded a dramatic shift. The intensity of solar particles dropped sharply, while the influx of galactic cosmic rays from outside the solar system surged. Magnetic field measurements confirmed the transition. Voyager 1 was no longer moving through the solar bubble, but through the plasma and magnetic environment of the galaxy itself. 6 years later, in 2018, Voyager 2 followed, confirming Voyager 1's observation. Interestingly, the two probes crossed the heliopause in slightly different ways, showing that the boundary is irregular and dynamic, shaped by the solar wind's interaction with the interstellar medium. The data revealed that the heliopause is not a smooth wall, but a rippling, turbulent frontier, influenced by magnetic fields and interstellar pressure. Now fully in interstellar space, both Voyagers are sending back invaluable data about the local interstellar medium. They are measuring cosmic rays, which bombard the solar system from distant stars and supernovae. Plasma wave instruments detect low-frequency vibrations in the sparse interstellar gas. Magnetometers track the direction and intensity of the interstellar magnetic field, helping scientists understand how our galaxy's environment interacts with and shapes the solar system. This is the first time humanity has been able to directly sample the space between stars. The Voyager's findings are rewriting textbooks and giving scientists a new understanding of how stars, their winds, and galactic cosmic radiation influence one another across the vast emptiness of space. Crossing the heliopause was more than a technical achievement. It was a symbolic leap. For the first time, humans touched the edge of interstellar space, using robotic explorers that continue to travel billions of kilometers away, silently sending messages back from the edge of the known universe. The Voyagers are no longer just spacecraft. They are ambassadors of humanity, carrying a record of our existence into the galaxy. As Voyager 1 and Voyager 2 crossed into interstellar space, they began sending back data that has transformed our understanding of the solar system's boundary. The edge of the heliosphere, which we once thought of as a smooth, bubble-like shield, turned out to be far more complex and dynamic. The probes revealed that the heliosphere is irregular, shaped by the push and pull of the solar wind interacting with the surrounding interstellar medium. It is not a neat, uniform bubble, but more like a turbulent, rippling ocean at the edge of our solar neighborhood. Within this boundary, the density and behavior of charged particles, the plasma, were unexpected, showing variations that challenged prior models of space physics. Voyager instruments detected plasma waves traveling through interstellar space, offering the first direct measurements of the medium that fills the galaxy between stars. These waves help scientists understand how particles and energy move through the cosmos, giving clues about cosmic radiation and galactic magnetic fields. Another major discovery was the dramatic increase in cosmic ray intensity beyond the heliosphere. The solar wind, once thought to gradually fade away, actually forms a protective shield, deflecting high-energy cosmic rays that would otherwise bombard the inner solar system. Understanding this shield helps us model not just the sun's protective influence, but also how other stars might shield their planets, which is crucial for studying habitability across the galaxy. The Voyagers also measured subtle shifts in magnetic fields, mapping the boundary between our solar environment and interstellar space. This data is refining our models of how solar systems interact with the galactic environment, and it provides clues about the life cycle of stars, the behavior of cosmic radiation, and even the formation of planetary systems. In essence, the Voyagers have turned the edge of the solar system into a scientific goldmine, revealing secrets that no telescope or Earth-based observation could uncover. Every reading, every particle detected, every magnetic fluctuation helps scientists understand not only our solar system's protective bubble but also the larger galactic neighborhood in which we live. These discoveries are building a foundation for future interstellar exploration, proving that even at the extreme limits of human reach, our curiosity and technology can continue to unlock the mysteries of the universe. Even after more than 47 years in space, both Voyager 1 and Voyager 2 continue to communicate with Earth. Though their energy is steadily declining, their radioisotope thermoelectric generators, powered by plutonium-238, slowly lose efficiency over time, forcing NASA engineers to shut down non-essential instruments one by one. Despite this gradual dimming, the data they continue to send back is invaluable, offering a window into interstellar space that no other human-made probe has ever reached. NASA projects that sometime between 2025 and 2030, the Voyagers will go silent for good. Yet, even after they stop transmitting, they will drift endlessly through the galaxy, silent ambassadors of humanity, carrying with them a unique and timeless gift: the golden records. These phonograph discs, carefully encoded with images, sounds, music, and greetings from Earth, were designed to communicate the story of our civilization to any intelligent life that might encounter them. From the songs of Bach to the laughter of children, from the structure of DNA to the sounds of whales singing in the ocean, the records are time capsules of human culture, floating through the cosmic ocean. Voyager's legacy is far greater than just their technical accomplishments. They revolutionized planetary science, giving humanity the first close-up views of the outer planets and their moon. They revealed the dynamic and complex environments of Jupiter, Saturn, Uranus, and Neptune, and exposed the unexpected nature of the solar system's boundary. Every discovery reshaped our understanding of planets, moons, magnetic fields, rings, and even interstellar space itself. Beyond science, the Voyagers inspired generations of explorers, scientists, and dreamers. They demonstrated that with careful engineering, bold vision, and persistence, humanity could reach beyond the sun's domain, entering a realm no human has ever seen in person. They set the stage for future missions to the outer planets, interstellar probes, and the long-term goal of sending humanity itself into deep space. Finally, the Voyagers serve as a profound symbol of curiosity and unity. They remind us that our small planet is part of a vast and mysterious universe, encouraging reflection on our fragility, resilience, and potential. Even as they drift silently in the darkness, carrying the sounds and stories of Earth, they continue to push the boundaries of human knowledge and imagination, leaving a permanent mark on history. The story of Voyager is not just a tale of spacecraft. It is a story of humanity itself reaching outward, seeking to understand, explore, and connect with the cosmos. As we watch Voyager 1 and Voyager 2 drift ever farther into the cosmic ocean, it's humbling to realize that two small human-made spacecraft are now the farthest objects from Earth, silently exploring regions of space no one has ever reached. They are a testament to human ingenuity, curiosity, and the unyielding desire to explore the unknown. Even when their signals fade and their instruments fall silent, the Voyagers will carry the voice of humanity across the stars, a timeless message that civilization once looked up at the night sky and dared to reach out. Their journey reminds us that exploration is not just about discovery, it's about perspective. From a tiny blue dot in the vastness of space, we see how fragile and precious our world truly is. Voyager teaches us that our quest for knowledge is limitless, and that even the smallest steps can leave a legacy that echoes across the galaxy. The story of Voyager is far from over. It continues in the minds of scientists, engineers, and dreamers, inspired to push further, go faster, and reach higher. And as long as humanity looks up, there will always be new frontiers waiting to be explored. So let the Voyagers remind us, the universe is vast, mysterious, and beautiful, and our journey has only just begun. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.